Hey, what's going on, everybody? How are you doing? Happy Saturday, chat. Hope you guys are doing super good today. We are going to kick things off right into some Kerbal Space Program. We are going to revisit our guidance, navigation, and control codes that we were developing earlier this year and late last year for KSP in Python. And we're going to see if we can't maybe improve, at least to some degree, our accuracy about getting to the pad. Because I think where we have things currently is we do align ourselves with the pad in terms of the vehicle's orientation. And so we do have that like lateral control. But what we don't have is the downrange control. We have cross range control, but not downrange control. So that basically means that we're always going to be pointing towards the pad, and if we end up going overshooting the pad, then we have to do a 180-degree turn, and then that just causes problems. So I'm going to see if we can't today implement a pitch controller for our vehicle, our DCX vehicle. To ideally keep us from overshooting. That's kind of the goal. Yeah, so I was kind of thinking about this earlier. I think how we're probably going to need to do it is have our pitch controller being affected by our downrange distance, and we're going to see how that works just like that. And then we're probably going to also need a horizontal velocity damping code, or like damping term. So we'll probably end up, well, maybe. We'll see first how the distance control goes, just using the pure distance away we are from the pad, to see how that works. And if it doesn't seem to be doing everything that we need it to, then we'll aim to probably bring a velocity term in there. To try and, because that's the thing, right? We need to make sure that we move towards the pad, but we also need to make sure that when we're really close to the pad, we start slowing down, which means that we start pitching up to try and prevent us from overshooting. So it can't be only distance determined. So I think we are probably going to need a velocity term in there, like a pitch control term for velocity, or horizontal velocity, to try and keep our horizontal velocity just from going up to 1,000, or some really high number, and us overshooting. So that's what we got in store today. We're gonna see if we can't get it done. It's gonna be a little bit of a shorter stream because I got some things in the evening, but we'll see what we can do in a couple hours. Got the good old-fashioned coffee with our rocket science mug. Let's see what trouble we can get into. So we're gonna need the HUV for our heavy utility vehicle, and that's going to need to be with the DCX, and we're going to get Anth Kerman in there. He's our ground crew, and let's go ahead and launch onto the VAB, and we'll kick it over into our landing pad slash test pad. And then we should be able to refuel it and see where our current guidance, navigation, and control lies. So this is what we got to work with right here. This is what we've been working on. This is the last state that we had it in. And from what I remember, it basically, like I said, aligns ourselves with the pad, but we don't have any actual steering control implemented for our pitch. It's just currently stating a negative pitch down moment. Basically just keeping a constant pitch, which is fine because that pitch angle does allow us to get forward motion, which is not a bad thing, but it's static. So that means that we can overshoot, and that's not good. So we'll see what we can do. We're going to move this over down the test range here onto our test pad. Our test pad will act as both the launch and landing pad. So we'll see what we can do with that. All right. I think I want to bring it over this way, and we'll kind of line it up this way with the pad. It doesn't exactly matter, but I think that's the orientation the control system looks for. but I guess we'll see. There we go. So let's go ahead and bring these down. Those are down. We'll now lock the motor. And now it's time to move us back. Something like that. There we go. Yeah, so this thing works out very, very well. It's modeled after the DCX, or the, was that a Lockheed? No, Northrop. Who did the DCX vehicle? I'm blanking. McDonnell Douglas, of course, the one prime I didn't mention. All right, let's go ahead, and now I want to open this down a little bit, and then we should be able to bring these down. And then now we should be able to undock and drive off. There we go. Perfect. And now we drive away, get us hunkered down into some decent area. So that'll be safe from any sort of falling vehicles and whatnot. And we'll go from there. All right, bring it around. Over this way, and we'll probably put it right here in this divot, and hopefully that'll give us some protection. There we go. There we go. Good enough, right? We're perfectly over the edge of the hill, but it's totally okay. So now we can use these tanks and fill us up. There we are. Got one. Now for the other. All right, there we go. So let's just see where we left off our GNC, right? So let's see. We do have this Euler integration method that allows us to try and estimate within a reasonable amount of accuracy our apoapsis so we can actually dictate when we need to start coasting, because we basically go full throttle, but we don't want to go full throttle all the way up, right? We want to hit some sort of specific apoapsis. So we use this Euler integration method to try and estimate that. Yo, what's up? How are you doing? Yep, back to the classics. We do a computation of our LOS angle. So that's our line of sight angle, not loss of signal. Line of sight is basically, if you're flying in a plane and you're looking down at a pad, that's your line of sight, right? So it's that vector, that angle from basically where you are to where the pad is. I don't think we used the rate calculation for that. I think we were maybe trying to. I don't think it was working. Some angle, compass heading stuff. Yo, Caesar Soup coming in with a Twitch Prime subscription. Much love to you, my friend. How are you doing? Hope you're enjoying the stream. Thank you very, very much. Happy Saturday to you. And let's see here. We set up the DCX vehicle information. We get our landing site, which is basically just our takeoff position, right? We just get our target latitude and longitude when the vehicle is on the pad. Love seeing programming KSP. Indeed. It's a lot of fun for sure. Oh, that's right. Yeah, so we get this hybrid reference frame, and this hybrid reference frame, if I remember correctly with how the KRPC mod is developed, I think this is the ECI frame, or Earth-Centered Inertial. I guess in this case it would be the KCI, the Kerbin-Centered Inertial Frame. So I believe that is, if I remember correctly, that's what this is for. I don't know if we actually use it anywhere, but that's what we had set up. We activate our engine after a countdown of 3 seconds. We make sure all the engines are good. All right, all this is just checking the active vessel, no problem. Okay, so our target altitude is 60 kilometers. So we should basically burn at full 100% throttle until we estimate that we are going to hit an apoapsis of around 60 kilometers. Okay, that's good. And then, yep, we're predicting our future apoapsis, so that's what that is all there. We enter a hover. That's right, we enter our hover mode. We basically target, you know, plus or minus a few thousand meters to our target apoapsis. We enter then a hover mode for a few seconds, and then the vehicle should... All right, so we're setting up all of our PID control loops. We're setting up our data streams. Yes. Okay, so then we enter our state machine for the rest of the vehicle's guidance, navigation, and control, all the way from apoapsis hovering all the way down to the ground, ideally. So mode 1 is hover at target altitude, and we hover for a certain amount of time, 10 seconds. At which point we then cut the throttle. We enter our descent and landing bird calculation mode. But before we do that, we make sure to pitch ourselves negative 10 degrees. We enter a positive, or I guess I should say a neutral roll. And then we set up PRD controls for roll control and yaw control. Do we actually use these though? I don't think we needed roll, so no, we don't have roll control. Do we have yaw control? And no, we don't end up using yaw control at the moment. Okay. All right, so mode 2 does our burn calculation. This is our hover slam calculation. Basically, how much throttle do we need at what specific time in order to land nice and safely after free fall. We basically wait until we are below 3,000 meters, and if we're above 3,000 meters, we calculate our line of sight, so that way we can point back towards the landing zone, and then we just head that way. Okay. Then we do our time to burn calculation, set up our altitude controller for landing, and then land. Okay, fair enough. You know, fairly straightforward. It's really more code than it really is doing. A lot more code than what we actually are doing, but it should be good. So let's go ahead and just see what this does right off the rip, shall we, chat? So we are going to hit play on the Python. We got a countdown, 1, and ignition. There we go. Vehicle's away. So this is all hands off right now. Vehicle is completely in control. I will turn RCS off because we don't need that. So yeah, now what we should be doing is our target is around 60 kilometers. So depending on how well our estimation, our Euler integration method is doing, we should see a cutoff. It will be after our 60 kilometer mark, because the reason why we're not just using the in-game's apoapsis as our target apoapsis for our ideal achievable altitude is because it doesn't take into account gravity, or I'm sorry, drag. It doesn't take into account drag on the vehicle. So that's why we created an estimation, basically an estimator, to where we're actually calculating our own apoapsis with drag involved. So that means that we should burn beyond the 60 kilometer mark. I don't know how far beyond, because we're accounting for drag during that entire ascent profile during coasting. So it'll probably shut down at like 62 kilometers, something, I don't know. Oh, 61, there you go. And so you see drag is acting on the vehicle, so that apoapsis is now going lower. We're a little bit off in our estimator, because I don't think that this is actually going to get all the way down to 60 kilometers as our actual apoapsis realized, but you know, not bad. Not bad for a simple integration method. And I don't remember what assumptions we made in that integration method either. We were using the equatorial radius. You see that, chat? So we were using a simple exponential model for the density of the atmosphere, and then we assumed our drag area. And so that is, that's why we are not quite as accurate. I don't think those things are given in KSP, unfortunately. At least they're not static, right? That's a key takeaway. So there's some variability in that. All right, now we should just be coasting all the way up to our apoapsis, which is going to end up being about 1 kilometer over our desired mark, but it's not bad. I'm going to turn the RCS on because what we're going to end up doing is then getting into a belly flop mode. Again, all of this is still hands off. We're basically waiting to get up to our apoapsis, at which point it should enter belly flop, very much like Starship. Close enough for government work, pretty much. So it should be coming down now, and then it should enter its hover mode. Waiting for the hover mode to engage. Still waiting for hover mode. There it goes. Now it's trying to bring itself to a rest. And there it's now hovering. And now it enters its descent. And because this vehicle goes so high, kind of like Starship, we actually do put it into a skydiving position, if you will, a belly flop back into the atmosphere, so that way we can increase our drag area. Hey, what's up, Dr. Longbells? How are you? How much do you think a smaller DT would help? We've actually tested that name. We're actually doing a very small delta time. I think it's operating at 50 hertz, if I remember correctly. Now, 50 hertz in game, the game is not operating at 50 hertz, right? So there's a reason. If the game could operate faster at a faster tick rate, then probably that would help. But the limitation is not the Python, the limitation is actually the game. I think our delta time in the game is like 0.1 seconds instead of 0.02 seconds, something like that. So there's a big discrepancy in the amount of measurements we get versus what we can calculate or what we can actually achieve. But all right, so now we are belly flopping, and so you'll see that we're right now aiming negative 10 degrees pitch. And so this is what I want to change, because if I remember correctly, what we're going to end up seeing here is we're going to end up seeing ourselves pick up a lot of horizontal velocity, and we're going to start moving towards the pad very, very fast, and then we're going to end up probably overshooting. And that's what then things start to get a little chaotic, because then it's got to do like a 180 degree turn, and then it just, this is not the most aerodynamic vehicle, so it can't really do a 180 degree turn. Yeah, it's kind of a mess. So we'll see. Right now we're looking good. One was DT, was it? I'll have to check. I'll check as soon as we see the result here. All right, see, now we're moving towards the pad, and we're moving towards the pad very fast because this vehicle actually does fly. It is stable, but yeah, you see, we are moving very fast, and we're about to overshoot, so it's gonna have to do a 180 degree turn. Yep. And it should do that. It should at least try. And we now pass it, and now you can see it turning. But it's not very aerodynamic. And so now we're basically flying backwards because it can't do a 180 degree turn with any sort of reasonable controllability. And now we're flying backwards. So now I'm actually putting in some control inputs, trying to get the nose down so we can start moving forward back toward the pad. And now we're too low in the atmosphere, so now it's entering landing mode. All right, so that's the problem that I want to try and fix. And now it should do automated hover slam. There it goes. Landing burn has begun. And there we go. Entering constant rate of descent. And touchdown. So not bad, right? We got no fuel remaining for that, so that's about as good as it gets on the calculation. But Yeah, if we could make it a little bit better on the return, we wouldn't burn nearly as much RCS fuel as we did. So that's what we get to try and work on here today. So yeah, you were saying the delta T. Where did we define delta T? Because that's the clock rate of 50 hertz. So we're sleeping at a clock rate. DT. Oh, DT is 1. Ah, DT is 1. Good call. Yeah, maybe. I wonder if that should just be clock rate. Well, maybe not clock rate, because like I said, I don't think this, I don't think the game's actually operating at a refresh rate of 50 hertz, but could be better. Interdasting, maybe. So you know what? Let's just test. We got plenty of ways that we can test, right? So let's make that 0. Yeah, let's try 50 hertz, because who knows, right? Because if we change that to DT, then that's going to be int for elements in range of the int time to apoapsis divided by DT. Oh, that's why. Okay, I see what I'm doing here. The reason why I had it to 1 is because it takes a long time to do those calculations, because it's basically running a bunch of simulations every time step to try and see what our apoapsis is. And so basically when you set this DT really, really low, right, you end up doing many, many more time steps in your simulation. And you're basically running a simulation within a simulation, so things can get bogged down. But you know what, let's try, let's try this and actually see what's affected by it. It might just end up running slower, but is that really a big deal? I don't think so. It could be a big deal, but I don't think it really is a big deal. Let's go ahead and reload that quick save. Yeah, so we were basically doing a simulation. So how that Euler step integration or estimator works, right, is these are essentially the dynamics of the vehicle. We have our altitude, which is just our altitude plus our velocity times time, which is basically our altitude plus our, acceleration at that point to figure out what within the next time frame our altitude is going to be. We do the same thing for velocity after actually calculating our acceleration. Basically, simple derivatives is how the Euler step, the Euler integration works. And then we have our force of gravity, which is the only force acting on our vehicle in this simulation, because we want to know how high we get when we coast. Because the whole point is we're trying to figure out when do we shut down the engines to coast with 0 thrust on the engines to get to an achievable altitude, right? And then we're returning our altitude and velocity, which is being used to make sure that we don't overstep our bounds and be able to cut the simulation when we actually want to. Yeah. Okay. I like it. Yeah, let's try it. Let's try a faster delta time then. Yep, we are fully fueled. Awesome. Good to go. Let's try it again, shall we? And let's see if we won't make any other changes except for that, because I am curious to see how a faster time step might work for those. Like real life? Exactly like real life, yeah. All right. So you can actually see, I think the gameplay is maybe noticeably just a little bit slower, because it's doing all those calculations in the background on my, the same PC. But it's not that, noticeable, honestly. KSP 1 for me always runs slow because we have so many parts in render range and stuff. And we are just about at green clock speed in terms of the sim rate. So yeah, we'll see if this is any more accurate. And then from there, we'll get into figuring out how we can improve the guidance. Really just want to try and figure out what's the best way to get our downrange control. Basically, how can we get our downrange position within our control, which is, within our pitch control. How can we change our pitch to bring us directly over the pad. What I'll also probably do on this next go around is not go so high because it just takes so long. It takes so long. It takes so long. All right, coming up on 60. There's 60. Oh. Interesting. So changing that to a much higher, I think it's because it's in the middle of a simulation. I think that's why. I think the simulation, our Euler integration is taking too long. And yeah. Very interesting. Very interesting. There you go. There you go. So yeah, it is a matter of balancing how fast we can do these calculations versus how fast the game runs. Which is why our delta time was so large. Because yeah, we ended up going 113 kilometers, chat. I wonder, just out of curiosity, what happens if we do that at 5? Will the accuracy also be really bad? It'll run faster, but I also wonder if being stuck in a simulation is also causing some issues with overshooting. I don't know. Things to think about. Yeah, let's reload that and try again, shall we? And this will be the last test. For whatever, whatever happens here, we'll probably bring it down to 1 unless a time step of 5 actually improves it, which I don't think it will, but you never know. Maybe with 10 hertz, yeah, we could probably try anywhere in between. But let's, I'm curious to see how going higher actually fixes it, or changes it, I should say. Generally speaking, you definitely want to do that, but also generally speaking, you have independent processing units able to run on your vehicle that's flying and giving you measurements. Where in terms of this, we're essentially running a simulation at every time step in the game. So, and we can only get the, yeah, I don't know. It's interesting. Either that or we should just end up trying to figure out how to do multi-threading in KSP. Or not in KSP, in Python, because I'm not using multi-threading. So if we can implement a thread pool or something like that to get all these simulations calculated out. I wonder if I can... Okay, no, I don't want to touch it. I was going to say, I wonder if we can physics warp. I know it'll remain stable, but that means that we end up, you know, our time step, so to speak, in game gets much larger in order to achieve that, so I don't want to mess any of those variables up. By fitting the arrow scalar in that function using flight data. Indeed, Names, that is actually something I remember us trying or thinking about doing, because I think we also maybe did something like that, because you can go into physics, right, and get the display arrow GUI data, and you can actually get things like your ballistic coefficient, and you can get your drag area and things like that, right? But unfortunately, this drag area, right, is not always the same depending on your angle of attack. Essentially, the angle your body is relative to the angle of the oncoming airflow. So that's why we kind of average it out. So I think we did end up using this to do that, but of course, there's going to be margins of error in doing that. So yeah, what would be really interesting, actually, now that you speak, like now that you mention it, is if we ran like 100 of these simulations or ran 100 flights, and then that 100 we were able to create a table of all the average values at like certain altitude markers. That actually could be really interesting. Does the gravitational parameter? No, the gravitational parameter will never change, but the force of gravity will change based on the vehicle, based on the vehicle's altitude and stuff, but the gravitational parameter itself does not change. Or are you seeing something here where it does? The gravitational parameter should be constant for Kerbin. The force of gravity will change as you burn fuel and as you get higher in altitude, of course. All right, we're coasting, chat. So where did we end up going? Oh, we actually undershot. Well, that's to be expected, right? Undershooting is to be expected because we were doing time steps of 5. So at each time step, we were updating our simulation in our Python code. And so we were taking really huge steps. So in that case, yeah, we actually undershot. So yeah, maybe we'll put it at like 0.5, you know, 2 hertz or something. 2 hertz is at least twice as fast as what we were having it before. And we'll see what we can do with that going forward. All right, entering our hover, or our landing orientation. Yeah, what's up, Junie? How are you? Can you talk politics? I mean, sort of. I guess it depends on what the politics are. If it's space flight oriented, sure. What's intense? How are you? How are you doing, my friend? Doing pretty good. Doing pretty good. No complaints. All right, we are in our belly flop maneuver. Is there a better name for that? I mean, that's essentially what Starship does. I feel like Starship and SpaceX coined the phrase belly flop, or at least the community did after watching how Starship falls back. It is a great way to stabilize your vehicle when it's doesn't have wings and stuff. Hey, Captain Failure, how are you? Oh, KSP 2, yeah, understood. Yeah, me too. For sure. I'm definitely huffing that copium big time, hoping that they're going to stick to their original word, and their original word was saying that KSP 2 is safe. But yeah, I'm huffing that copium big time. We'll see what actually happens, of course. And it was right about to have a patch that was going to fix so many of the like tiny bugs that are in the game right now. Like all of like the orbit lines disappearing sometimes, or the error in your vehicle's landing state causing issues and things like that. Like some of those that were kind of routine but like annoying, we were going to get a patch that fixed those. Unfortunately, no such luck, I suppose. All right, trying to get back towards the pad, but we are going to overshoot again. Of course, we did in fact overshoot. I'm going to do some manual control inputs, trying to get the nose down so we can head back towards the pad. There we go. Let's see, this is what I wish it would do automatically, autonomously. It looks like we're going to overshoot again. Yep, we're going to overshoot again. So we're going to land probably over here or something, because now it's going to go right into landing mode. Yep. Yep. All right, well, we kept it within the KSP proper. That's good. Semi-ballistic, yeah. A technical name for the orientation, yeah. Local horizon. And there is that, looking good. And boop, nice and safe. We did a little bit better on our fuel consumption that time. All right, well, not bad, right? If you have contract to build base on the moon, for example, you have to join all parts on the surface of the moon in order to accomplish the contract. You'd have to give me the contract wording, Andrew, but to my knowledge, unless it says all at once, I don't think you have to. Can somebody in chat help Andrew? It's been a long time since we've actually done a contract in KSP 1. This is career mode. Everything we're doing is in career mode, but it's just been a minute since I've worked on like the moon-based contract and stuff. I don't think you have to connect them on the surface. Yep, easy peasy. All right, let's go ahead and bring it back, chat. So we are going to keep our delta time on the integrator to 0.5. That's 2 hertz. Basically 2 times a second. And let's start looking at how we are going to implement our pitch control. Because right now, as you guys can see, we only have our heading being updated, and our heading is basically just a compass heading to always direct us towards the pad. And we're computing our line of sight angle, and essentially that is just the angle between our pointing vector and where the pad is. And so we always we calculate our compass heading based off of that difference. If the contract is to put a base on the moon with XYZ parameters, then it does have to be one vessel. If you do it in separate pieces, then you gotta dock them, yeah. But you can dock them beforehand, right, Intense? So like you can do 5 launches, construct it around the moon, and then land it, that sort of thing. After the first overshot, it should aim the nose directly at the pad from there until burn time. That's not a bad contingency, Warlock. Ideally, in a perfect world, we don't overshoot in the first place, right? That's kind of what my philosophy on that, but yeah. 19 Kerbals, science modules, 6,000 liquid fuel. Yeah, so Andrew, you should be able to do that in multiple launches. You will just have to construct the base on the moon or around the moon. You just have to have the base, you have to have all of those pieces, right, connected together. However you do that, I don't think it matters. I do want somebody in chat to confirm that, Intense, if that's what you were saying. Like, I think how I did that sort of similar contract was, you know, I ended up building my base actually around Kerbin and then put a tug on it to then send it out to the moon, and then I landed it on the moon and the contract was complete. But I built that base in multiple missions or multiple flights. I think that's how you should be able to do that. What about adjusting pitch to control for velocity, limit targeted for velocity to try not to overshoot? So I think that is going to be a portion of what we do, Names. So if we weren't, for those of you that weren't in chat when I was kind of discussing my thoughts earlier, what I think I'm going to do is create 2 PID controls. One on our distance to our pad, so our physical distance to our pad, and then another one that's going to be basically a damping portion, which is going to be our velocity PID, our horizontal velocity PID to be specific. And so I'm pretty sure that if we add the 2 together, depending on how far away we are from the pad, we should, like if we're very, very far away from the pad, we should nose down pretty hard to gain our horizontal velocity, right? And then once our horizontal velocity is pretty high, we should then start to pitch up. So I think that could work by doing basically cascading PIDs, where you have your distance PID, which could be commanding -20, but if our horizontal velocity is huge, then our horizontal PID is going to be commanding +20, right? Or something like that functionality, I think is how I want to try to do this first. I'm sure there's, you know, always more than one way to actually do any of these sorts of control loops, but some better than others. But that one to me is fairly intuitive and should be fairly easy. But let's figure out recovery from overshoot and then tune that. Yeah, that's fair, Warlock, that's fair. Yeah, I mean, you know, there's always things that we can do as well. Like we can implement a keep out zone from the pad, say like 100 meters radius, or, you know, like a 100 meter radius keep out zone. And the vehicle should never enter that radius, so it should always go around, right? So that way it's not trying to do a 180 degree turn. Yeah, I mean, there's lots of different ways. Or, you know, if it does, then we just limit the change in yaw and roll in order to account for that, so it's not so drastic, so it actually gives time to turn around. There's definitely lots of little things that we can do here and there. Make sure to interpolate target distance from starting offset to 0 after cascading PIDs. Yep, that is true. I'd want to match time to burn to time to be directly over the target. That's also another way to do it. And I was trying to think about how I would do that in the first place. So time to burn would be our landing burn. Right now, we basically enter a vertical basically pointing straight up once we exit our 3-kilometer altitude gate. So I'm wondering if, well, we could always, because our time to burn is for 0, is for touchdown. So you know, landing at T0. Yeah, you know what? There's definitely lots of ways. Let's try this way first, and we'll see how accurate we can get. We can always build on this in the future. So I think the first thing that we're going to need to end up doing is figuring out our PID loops, right? So we did build out a PID class here in Python, and it's pretty simple. It has everything you need for, you know, clamping your outputs, which is really, really useful. For updating and everything based on the error and setting your target points and things like that. So we should have an example like this one right here. And where do I want to do this? Let's actually do this down here. We're going to need 2 of them. The first one is going to be the distance control. Let's call it the distance controller. Actually, let's call it the dist controller. And then we're also going to have the horizontal velocity controller. And it should be PID max, min max. Okay, cool. Our deadband, yeah, it can be really, really small. Our deadband probably doesn't need to be anything, honestly. Control, let's make this for the distance probably pretty small, because our distance is probably going to be in meters, since we're also using meters per second for a horizontal velocity. Probably don't need an integral, might need a derivative term in order to make sure we don't overshoot. Basically tries to limit our overshoot. And then we're probably going to want to do a maximum of -20 pitch down and a maximum of +20 pitch up. And then similar for the HVEL, let's start this off at 1. Maybe not 1. Let's actually start it off at 0.1. Integral, let's actually give it a small integral term as well to try and reduce our steady state error. And then it probably doesn't really need a derivative term, but we'll start with that. And then same thing for this one. We'll do -20.0. Let's actually make sure these are all floats. And then this will be +20.0. Deadband, never going to be an issue. Yeah, what's up, Misadventures? How are you? Alrighty. Oh, now that could be interesting, Warlock. Instead of doing that altitude gate at 3,000, whenever our distance, right? Whenever our distance is within, I don't know, 50 meters or something like that, then enter that hover mode, or enter that landing mode. That could be interesting too. Yeah, there's ways. There's ways, chat. So many ways. Yeah. Okay. Yes, lots of ways. Many a ways. Yeah, okay. So we have our distance and our horizontal velocity controller set up. Let's just go ahead and comment this out because we don't need to do that. Let's see, what else do we have? That's all fine. That's all fine. Okay. Yep. It's gone asymptotic. Yeah. Last I heard it was on the 25th. Has it been pushed back again since then? Boeing has been having too many incidents lately? Really? Are you just talking about Starliner or Boeing in general? It's 25th? Yeah, okay. But yeah, they definitely have been pushing it back, huh? All right, let's see what we got here. Chat. that's all our time to burn, so it's gonna have to be here. So we get our current position, we have our heading, we're gonna need to get our distance to the pad, right? Like that's gonna have to be, so if we have latitude and longitude, is it the what is it called? Haversine? Is it the Haversine formula that we need? That outputs, or that can output the distance? The angular distance between 2 points on the surface of a sphere. Haversine formula. That's what I want, right? To change latitude and longitude. Latitude and longitude, and we can get our distance. Yes, okay. So this is what I essentially want then. Cool. Let's move that over here. No, it should be the 25th of this month. Should be the 25th of this month, don't you worry. Okay. So next week. Fingers crossed. Let's just put it below all of this. All right, so let's do define our Haversine distance, and we are going to take in basically our 2 latitudes and our 2 longitudes. So we'll do lat 1, lat long 1, and lat 2, long 2. All right, so then looking at that formula, we're going to need the radius. Okay, so let me see, radius Kerbin. What's the radius of Kerbin? Uh, 600,000 meters. Okay, 600,000 meters. Perfect. So yeah, let's do that. So that's going to be our R is going to be 600,000. And so from there, we're going to need to define our angles, which is really just going to be our latitude and longitude. And I'm pretty sure we're doing that in degrees from the game. So we're going to have to do that in radians. All right, so we're going to need to import, or should be from math, import radians, and I assume we're going to need, yep, sine and cosine. Is that right? Yeah, we're going to need sine, cosine. We're going to have a square root and then an a tan 2. A square root and then an a tan 2. Yep, perfect. And then coming back to our Haversine formula. All right, so it's a, so we're going to need to first multiply. No, okay, so we have our radius. C is going to be 2a tan 2a, and a is going to be sine squared delta lat. Okay, yep, that's fine. All right, so then that means that we're going to have phi 1 is going to be equal to our, what do they say? It's going to be our latitude, and then our longitude is going to be, we only need the difference in longitude. Okay, so we need it to be radians of lat 1, and then we also have phi 2, which is going to be radians of our lat 2. And then we're going to need our delta. Is that right? We're going to need our delta phi. Yeah, we're going to need our delta phi, which is going to be our latitude and radians, as well as our delta longitude. Okay. Tangent. That's right, tangent. What's up, Thomas? How are you? The hard part is calculating angular and direct velocity between 2 vertices in real time. Well, that's true. Yeah, we'll see. We'll see if we can kind of sort of get around that a little bit, question mark. Because I feel like this way is pretty simple, especially with what the game gives you. But yeah, so we have our delta phi is just going to be the difference between lat 2 So we're going to get in radians. We're going to have lat 2, or it just could be phi1 minus phi2, lat 2 minus lat 1. And then we're also going to have to do the same, I think, for, yeah, we're going to need, let's call it lambda. Is going to be radians of longitude 2 minus longitude 1. Okay. Let's just call this longitude. So we have lat and long. So then we go, so we need to calculate our A, and so A is going to equal sine of our delta phi, and we're going to need to divide that by 2, and then we're also going to have that be to the power of 2. All right, so that's that first term plus cosine of phi1. That's the second times cosine of phi2. And then we're going to multiply all of that by our sine of our lambda, which is the difference in our longitudes. And we're going to also divide that by 2 and multiply that squizzled. All right, so I think that's right. So to check, just to check the work here, we have sine squared of delta lat divided by 2 plus cosine of lat 2 times sine squared delta long. Yeah, okay, perfect. So far so good. Excited for another new Shepard flight tomorrow to see Ed Dwight finally go to space. Indeed, it is going to be good. But since we're single, yeah, that is true, since we are single-threaded. Which might be worth looking into upgrading here in the very near future. All right, so now we need to have our C. So C is going to equal 2 times A tan 2, which is going to be the square root of A, and the square root of 1 minus A. Okay. And then finally, we have our distance is going to be R times C, and we want to return that distance. All right. So that should be everything that we need. So we have C 2 times A tan 2 square root of A square root of 1 minus A, and then R times C. Perfect. All right. There we are, chat. There we are. So let's go ahead and exit out of that. And good. All right, so that's the Haversine formula. So the whole reason why we're doing the Haversine formula here, chat, is we calculate, and also the game gives us as like a measurement, and you can kind of do this from like GPS in real life, is getting your latitude and longitude. And we're doing that for our landing site, which is here. We're doing that for our landing site, and then we're also doing that for our vehicle down here, current position, latitude and longitude at each time step as we're descending. So we're basically getting 2 latitudes and 2 longitudes, and we are now trying to get the actual distance value in meters that we are actually separated from the pad, ideally in a perfect world, chat, right? In a perfect world. So I think from there, in order to move forward, we should have to come down here, mode 2, and yeah, so here. Actually, you know what? Let's go ahead and wait, what did I say? Update control inputs. Okay, so let's go ahead and now do some compute pitch parameter inputs. And so we are now going to have our distance to pad is going to equal our Haversine distance, and that is all going to take in our current position 0, our current position 1, and then our landing site 0, and then our landing site 1. Okay. Perfect. And before I forget, let me actually go up to here. And I want to change this to say 15,000. I want to do that so that way we don't have to wait so long to actually start testing this stuff, right? And then, yeah, let's just go ahead and make sure that at each time step we're printing out our distance to pad, just so we can make sure that that is working. So that's going to be our distance to pad. And you know what we could do way up here before we even get into it is we want our distance controller set point to be equal to 0. And we want the same probably for our HVEL controller set point equal to 0. All right. Not bad. Not bad. 0, 1, 0, 1. Okay. So I think that might be good enough for now. We could do the velocity input if we want to, but oh, maybe we can actually just go ahead and do our implement our control just so we can actually see what our control is going to be. So vessel dot target pitch is going to equal pitch input, and then we're going to calculate our pitch input to be equal to distance to pad, and let's just call it plus our velocity pitch, and we'll currently define that velocity pitch to be equal to 0 times, and that's going to be our HVEL controller, and we're going to need our current horizontal velocity or current horizontal speed. It'll be a magnitude because that's how the KRPC gives it to you. So it'll be vessel dot flight. Let me actually look at the documentation real quick. Under flight. It should be vessel, yeah. The vessel dot flight, give it a reference frame, and we're gonna want the horizontal speed. Okay, so it'll have to be vessel dot orbit dot body dot reference frame. Is that right? Vessel dot orbit dot body dot reference frame. Cool. And then we're gonna want that to be dot horizontal speed. Horizontal speed. Okay. You know what? Let me actually just take that out, because I'm going to want to manipulate that later. So we're going to call this our horizontal velocity, our current horizontal velocity. Okay. Or speed is probably the better one. Well, you know what? Actually, we could probably figure out a direction. If we're moving towards the pad, meaning our distance is getting smaller, then make this negative and otherwise increase it, right? That's probably the better way to do it. Or, well, that's probably the simple way to do it, not necessarily the better way to do it. Horizontal speed. Okay, that should be fine there. And we're just going to have it be 0 for now. And then we're going to want this to be current horizontal velocity. And pitch input is going to be that. So right now we should only be focusing on the distance to pad, but let's also look at the current horizontal velocity, and let's print both of those out. And then I guess we can also actually print out our pitch input. Oh wait, no. That is not what I want to do, chat. That is not what I want to do, actually. We have our velocity pitch, and this isn't going to actually be our distance to pad, right? We actually need our PID controller to essentially compute our yeah. Because this should actually be our distance pitch. So our pitch angle based on our distance to pad. So let's go ahead and do that. So that means distance pitch is actually going to be our distance controller, and we're going to be updating that with respect to our distance to pad. Okay. That seems better. Let's go ahead and save that, and then let's go ahead and launch it and see what these outputs are. So we should only be going, oh, yeah, right. And let's actually, so we have distance to pad, current. So let's go ahead and do distance pitch. We'll also do velocity pitch. And then we'll also do our current pitch, which will be our pitch input. Okay. All right, let's see. And we should be going only up to 15,000 meters, is that right? Yeah, there we go. Let's see what happens, chat. Let us see what happens. Just on the green clock scale. Pretty good. Let's see how accurate we are with our apoapsis calculations at half of our previous duty cycle for our delta time, our calculation frequency. There's 10, looking for 15, and we'll probably be more like 16, ideally. There we go. Let's see how, ooh, we're slowing down pretty fast though. We're gonna undercut it by a little bit. Not bad though. And I think that's because our drag, actually not too far off. I mean, only 50 meters, I'll take that. That's your not normal hypergolic DCX, exactly. Yeah, so we're only 60 meters off of our estimation. So does that mean our drag calculation isn't enough, perhaps? We'll see. Should enter that hover, there it goes. And then we should wait for it to enter the belly flop. There we go. Oh no. All right, so we had a break in the code, chat. What did I do? Distance controller, distance to pad, PID object is not callable. What? I mean PID is not callable. Do I need, oh, did I just do, did I not do update? Oh yeah, I did not do update. There we go, that'd be that problem, chat. Oops. There we go. This is fine, right? This is fine. Sure. What could possibly go wrong? Not bad. Not bad. It's like it landed itself, chat. How about that? All right, let's try that again though. Oh, but we did not have engines shut down. Our engines did not shut down. Oopsies. All right, let's roll it back. Let's try it again. Should be okay. I wonder if we're going to need a low pass filter involved. I guess we'll see. I don't know how fast the distance pitch controller will be commanding, but we'll see. All right, we're away. Go ahead and time warp. Get up there a little bit faster. Go ahead and stop right there so the calculations for the apoapsis aren't affected. There we go. Oh, look at that, chat. Look at that. 19 meters off that time. Awesome. There we go. Sweet. Easy peasy. There we have it, chat. Our calculations. So distance to pad, horizontal velocity, our pitch with respect to distance, our pitch with respect to horizontal velocity, and our pitch with respect to everything combined. So that looks to be working. We are actually moving further away from the pad though, but we are starting to slow down, but our pitch is -11. Looks like we're doing pretty good there. All right, pitch is now -9, looking good. As we're moving closer, pitch is now -6, -5. Horizontal velocity is huge though. Yeah, horizontal velocity is huge. All right, since we passed it, I'm gonna stop. And let's rewind. All right, let's take a look at the logs here and see what we got. So after, I wanna see what it is before passing. So we got within 7 meters of our cross-range distance, or I should say our downrange distance. And it was starting to command to positive. Oh, it was commanding some big swings. Yeah, it was commanding some big swings here. So I'm wondering, you know what? Let's actually implement a low pass filter then. Yeah, we already have it here. How do we want to do that? I guess we'll just, wait, do we already have one somewhere? I don't think we do. All right, let's do it. Let's put it right here. Let's do pitch LPF. It's going to equal LPF. And then we'll do, sure, 4, 3, and then our clock rate, which should be DCX dot clock rate. All right, we'll see if that smooths it out, putting in a low pass filter, because then what we should be able to do is come down here, and for target pitch heading, we want it to be pitch LPF of that input. I think. Is that right? Yeah. Yeah. Okay, sounds good. And what was this one defined with? Because that smoothed it out pretty well. And that was 4, 2.5, and 30. Okay. We'll leave ours at 4.3 and see what happens. Okay, let's try that again. But you guys see, you know what? Let's actually start implementing our velocity damping term. And I think we're also going to want to do a sign on the horizontal velocity to figure out if we're going further or away from it. So let's see this. Let's do previous distance is going to equal 0, and then we're also going to have velocity sign is going to be equal to -1. Okay, so that means here we actually want our current horizontal velocity to be the velocity sign times that, and then do it down here. So if our current distance to pad is greater than our previous distance, so if our current is larger than our previous, we're moving away. So then velocity sign is going to be equal to -1. And then else if, or I guess it could just be else, right? Else if distance to pad, which is our current, is less than our previous distance, then we're moving towards it, so our velocity sign can be equal to 1. Oh, I guess I actually didn't need that, did I? You know what, we'll just comment that out. Leave it as a comment so that way we know. There we go. How does this integrate with KSP? So Tensile, I'm using in Python a package called KRPC, and then KSP actually has a mod called the KRPC mod. So you can go here, KRPC, or Kerbal Remote Procedural Calls, and it tells you how to set it up, all the APIs and everything to do. So you need two things. One, choose your programming language, because it does offer support for a few: C Nano, C Sharp, C++, Java, Lua, and Python. I chose Python, and then from there learn how to install or use the different packages or modules. So yeah. So you should be multiplying your horizontal velocity by a factor to enable you to make better corrections farther out. This will automatically dampen the closer you get to the target. That will fail if distance to pad is equal to previous distance. That is true, it will. It truly will. So yeah, we will do an else if then. Wait, but it's an else statement. What do you mean? What do you mean it'll fail? I mean, if distance to pad is equal to previous distance, and our distance is 0, so it doesn't really matter what the sign is, right? Well, I guess that's not true. It'll be positive, meaning we're still moving towards the pad. So I think that's okay. I think that's okay, yeah. Yeah, absolutely, Tensile. All right. Yep. So now our current velocity should be reflected by the sign. We can now get our velocity pitch involved as our damping term. And that should now be in our pitch input. And I think this actually might need to be negative, because we want it to pitch down if it's positive, right? We essentially, so what this is saying is if our velocity is positive, we're moving towards the pad. But what that should actually mean for our pitch PID output, it should be negative. It should be the opposite of that sign, I think. We want it to pitch down if it's moving away. We want it to be... I think that's right. Anyways, let's try it. We can always just switch the sign if we need to. Alrighty. And we're away. Alright, so we're going up to 15 kilometers again. There we go. We'll wait for it to start outputting all of the things that it needs. Yeah, because I think we need that negative there, because if we're moving forward, it's going to be positive, but we don't want it to command a positive pitch angle unless the velocity is too high. Then it should start pointing down. I think that's right. We'll see. All right. There it goes. So we were 800 negative. So we are moving away from the pad, and we are pitching down relative. Okay, nice. So I think we got the sign right. Because we're moving away, so we're pitching more down, and we're commanding now negative 14 degrees. We're now 1,000 meters away. Still commanding negative 14. We could actually probably improve or have a larger gain on our velocity PID. All right, we're starting to move towards it. But we're not getting a negative. We're not getting, we didn't switch the sign. Why? Did we just already go past it? Oh no, I should have put our control system on. Stand by. All right, stop. Whee! This is fine, chat. DCX, total loss of control. I want to see what this is doing here. So this is obviously... Did I update it? Oh my god, I'm so silly, chat. So silly. Previous distance isn't getting updated. There we go. Previous distance should now be equal to distance to pad. That would probably help. So we actually weren't updating our sign ever. Silly me. I'm also wondering, because if we look back at the thing here, when we were going negative 80, oh, well, negative 80 was commanding positive 12, or it should have been commanding positive 12, because the signs are wrong, right? Because we're moving towards the pad with 80 meters per second of horizontal velocity, so this should have been trying to do 12 meters positive. I think that's fine. Yeah, we might need to play around with the PID loop a little bit. But overall, let's actually look at the output on our low pass filter. Ooh, look at that. That's actually really, really stable. We could actually probably even make it a little bit shorter to pass out some extra. Yeah, because we did have a big jump there, so we can actually probably even have a better low pass filter, a more stringent low pass filter, I should say. Which, if we go back to our digital filter.py, if we use this, that's what that looks like. But then if I do, say 1, does that make it faster or slower? Slower, okay. So yeah, the slower, we can probably do 2 here on the low pass filter. And that should bring it in pretty well. Yeah. Oops, FTS button, indeed. Probably up the amount of pitch that can be commanded. Yeah, we'll see. Probably though. I just want to make sure all of this is in line first, and then we can start tuning it. I think that's all that we need. Oh, let's see. No better way to know than to test, chat. You must verify. Validate. All right, see what happens. And we'll go a little faster here. Coast up to 15 kilometers. There we go. Let's see how accurate that is on that 15-kilometer mark now. It's looking pretty good, honestly. 60, 40 meters off. And all right, we're gonna undershoot a little bit here, but we're almost there. What are we gonna be, like 50 meters off of our estimate? Or off of our desired? Not even 50. Ooh, I'm happy with that. Yeah, only 33 meters off of our desired. Pretty good. Not sure this flight software is certified. Nope, not even close. It is Python, and you will not ever certify Python for flight. Well, I guess it depends on if you're trying to follow a standard, like the DO 178 standard, which is the required software development standard for human spaceflight. That is a monster, and no, Python is not even able to be certified for that. Not even close. All right, let's take a look here. We're moving away. We are indeed showing that we are moving away at negative. That's good. We are commanding 17 degrees pitch. Is that not right? But we're only doing negative 10 here. Why are we only doing negative 10? Okay. Stand by. We are now moving towards the pad, and we should now be commanding up. We are moving towards the pad, and we are trying to pitch up, and it is not working. Why? Oh my gosh, I'm so silly, chat. So silly. Why doesn't that error? I don't understand why that doesn't error though. If vessel.autopilot.targetPitch is required, then why does the vessel.targetPitch not be like, hey, there's no attribute for vessel called target pitch? That doesn't make any sense, chat. But hey, we at least are gonna land this safe and sound. That's good. Up, up, up. Okay. Yep, we stuck the landing. That's fine. All right, but that all works now, chat, which is fantastic. Yeah, see, we're negative here because we overshot the pad, and so we're commanding negative 21. And then here, we're going super fast and very close to the pad, so we're trying to pitch up as much as we can. So, nice. Hashtag Python, indeed. But, like, why, what in Python would ever make that okay? Right? Because we're trying to set an attribute of a vessel to a variable, and that attribute doesn't exist? Question mark. So like, how is that even possible? Like, if the class is defined and it doesn't have that attribute, then why can you just set it? Why can you set a non-existent attribute to something? It must exist but not be used, I guess. I'd have to look at the Python API for KRPC and see if there is a vessel.targetPitch, but whatever. I don't know. It's weird. See, it's things like this why Python is not for human spaceflight or for human anything. For critical systems. Yeah, I guess so, Warlock, but I don't understand, like, because so the class is already defined, though. But we went a little over, because I'm fast-forwarding everything, but anyways. Import certification, stop. You hush. All right, let's see what we got. What languages they use in real life? Typically C, C++. just because that's been the standard for 50 years now or whatever, and because it's been such a standard, they have so many they actually have standards written for it. Like if you look at here, we'll just go on a slight tangent here while that's just going to be running in the background screaming, why am I not moving? Boop, and boop. Nope, stop it. Just bring me over here. So if you look at DO-178C, this is a specific standard for software, specifically for airborne systems, for human-rated systems. They use it in human spaceflight. This sort of standard requires a very specific, based on the I guess the criticality of the software. So are humans involved? If there are humans involved and this software fails, are they going to die, right? So that would be catastrophic failure condition. They actually dictate the types of compilers that have to be used, because you have to trace everything to a very specific way a compiler is implemented. So they literally have like 50-year-old C++ compilers that are specifically meant to compile your code within this standard, because it's so rigid, of course, because there are human lives involved. But DO-178C is typically for human applications, especially for flight. There's a whole bunch of these as well, like DO-224, I think, is for how to develop ground systems, or like ground software, test software systems. There's a whole bunch. There's a whole bunch of stuff. That's just the one I know because of space flight and stuff, but yeah. Are we playing Pokemon? All right, we're chilling, chat. We are chilling. All right, we're still moving away from the pad. That is correct. We are commanding -8 degrees pitch. Awesome. We are now starting to move towards the pad. Still moving towards the pad. Still pitching down, moving towards the pad. Awesome. Nice. We're now basically pitching 0 degrees, and it's actually pitching 16 degrees, and we're not gaining much more horizontal velocity. We're still moving towards the pad, and now we're entering landing burn, but we're going to be a little ways away. But hey, that was so much better, chat. So much better. This time we didn't undershoot or overshoot, we undershoot a little bit. We had a little bit of an undershoot. There you go. Not bad. Okay, so I think that means we can probably possibly for, we might want distance to play a little bit of a larger factor. As soon as we started programming, we found to our surprise that it wasn't as easy to get programs right as we had thought. Debugging had to be discovered. I can remember the exact instance when I realized that a large part of my life from then on was going to be spent finding mistakes in my own programs. Nice. 1949, gross. Did you F-string and round those printouts? Yeah, you can. Certainly names. You know what? I actually haven't had to do that in forever. Let's see here. So print F, and then it would be 0.2 float. Okay. So print, we want to do print F. Something like that, right? And then we need desired. So distance to pad, yep, and then this, and then dot to F, right? I think that's right. Then we essentially need that on all of these. Okay. Oh, it's off the screen. I was like, why can't I see? There we go. Cool. I think that's how it's done, right? Oh, it looks like it's supposed to be done. All right. So not bad. Not bad. Let's tune our PID a little bit. Let's see if we can't get a slightly larger distance controller involvement here. I still want our horizontal velocity controller to be the larger one, I think. Probably even increase that by 2. So I definitely want to increase this one and maybe increase that one a little bit. And yeah, let's see what that does. So now it's pretty much just a matter of tuning to see how close we can bring it to the pad. But then the only thing to remember, right, Chad, is that this is a linear controller, and linear controllers are, of course, really good at doing the same thing over and over again when nothing changes. But as soon as we try to, you know, make this go up to 60 kilometers altitude, its maximum apoapsis, then I'm sure we'll have to retune it. So don't want to spend too much time on this yet, but I do want to make sure it's all working. Guess what? We can actually just refuel it right here, right now, chat. How about that? You don't have to redo it all. There we go. Cool. All right, let's try again. But how do you get real-time data from the game? So Keo, is it Keo or is it just Key? You want to look up a mod called KRPC, and you want to install that mod KRPC in your game. And then if you just Google search KRPC, you should be able to find the documentation. And it's basically an API for a bunch of different coding languages. Python is what I'm using, and you can get all of the data through that API. So it allows, so basically it's a remote procedural call implementation in Kerbal, which allows you to communicate with Kerbal using code and stuff. All right, let's see what we're gonna be able to do here. Yeah, perfect. All right, so there we go. We're gonna be a little bit of an undershoot again. That's fine. So I think that means either our CD times A is a little bit too low. Actually, look at that. We're actually going to be perfect. Never mind. Screw what I said. We're gonna be 27 meters off of our calculation, off of actual. That's pretty solid. I'm happy with that. All right, entering hover mode. And belly flop. There we go. Cool. Aiming back towards the pad. Make sure that these are good. They are now. Perfect. There we go. Commanding -22. Awesome, chat. That's actually fantastic. All right, but we might actually want to bring our... it's starting to pitch up. I think we gave our distance a little bit too much effect, because now our horizontal velocity is huge, and it's still trying to point nose down. Oh, there it goes. It's trying. but now we're going away from it. It actually managed to do that pretty well. Now it's commanding -20. That's actually really clean. Hold up. And now we're entering landing mode. Oh my god. Now I know it's hard to see because we ended, so remember chat, the landing site is where we take off from, and so we took off from over here. We got to reload that and see how that goes and see how that actually plays out. Oh man. 26 meter, 80-ish feet, yeah. Yeah, pretty much Teague. Yeah, multiply by 3.29 or 28, 3.286 or something like that. That seemed to work pretty darn well. Let's reload that and try again exactly as is. I think I do want to tune down our distance PID a little bit from where we did, because I think we increased it like by 5 times, and that's clearly way too much. Okay, let's see here. By the way, our low pass filter is doing fantastic. It's doing really pretty good. Yeah, I like it. We could actually probably even improve it even a little bit more if we wanted to make it smoother, but I think I'm good for now. What were we doing? PID, right here. So yeah, let's bring that down to say 0.3 instead of 0.5. Yeah. And this can probably be 0.3 just to have a little bit more of an effect. And let's go with that. 280, thank you. Thank you, Captain Crash. Pi feet, 3.14165, right? Yeah, it actually was manageable, Warlock. Because as it goes past it, it now wants to pitch down immediately, which is fantastic. It's not way too much, it's a little bit too much, true. Yeah, we'll see. We cut it in half, I think, from what we had, right? Is that right? No, not even in half. Yeah, we're at 60% of what it was. And we also increased our PID controller by 33%. Okay, pretty happy with that though. All right, let's see how accurate that one was. That one looks like it's going to be an undershoot. Or maybe not. Man, whoever it was, who was it in chat that started talking about changing the Euler integration delta time? Now, see, the thing is, again, it's simple Euler integration. So I wonder how accurate it'll be for very, very long distances, large coast periods, but pretty good. 40% reduction, yep. That's why I said 60% of the value, right? The opposite. All right. Oh, come on now. There we go. All right, so we're moving away. We're commanding very, very negative pitch. Keeping it pretty smooth as well. Awesome. Yeah, we're maxing out our distance pitch. Uno reverse. Yeah, that's right. All right, we're bringing our horizontal velocity up. Horizontal velocity PID is starting to pitch up, so we are mitigating our pitch. Very nice. 700, we're starting at 0 now. We're starting to pitch up. Oh, chat, this is going to be really pretty good. We're still going way too fast. I'm wondering, we're going to be able to manage this as we get closer. We're slowing down. We are slowing down, chat. We're like right over it. Entering, oh my lord. Okay, entering Oh my god. Not bad for simple PID controllers, chat. Wowzers. Yeah, I haven't touched it. This is all autonomous. We are not going to make it on the landing zone, though. Like, come on. We're going to miss the landing zone by that much. We took off from there. I like it, chat. I like it. All right, well, I guess we gotta go higher now. Now, see, what I'm also wondering, though, it was still commanding negative, even though we were super close to the thing. So how do we manage that, chat? Because see, it's still trying to command negative pitch for the distance controller, even though we're like essentially right on top. And I would think, well, no, that actually makes sense, right? Yeah, no, that actually does make sense. I think the way that it's set up right now, our distance controller is probably never going to require a pitch up because our target is 0. Our target point is 0, and we're always going to be away from that. And we're never going to be negative, so the sign will never flip. I think that's why it's so close to 0, is because it's never going to command a pitch up. So it's actually requires the horizontal velocity controller to do the pitch up. Bigger derivative. Nailed it! Auto landing, yep, all autonomous. Can you reduce the amount by how close you are so the adjustments get finer and finer? Yeah. Yeah, potentially. I mean, we could do like gain scheduling. We could do that. We could even get into optimal control. I mean, how SpaceX, I think, does it is uses convex optimization. But that's a whole can of worms, chat, is figuring out your boundary value problem and things like that. There are papers on being able to do that sort of thing. But I don't know how to do that offhand. These are just simple controls. That's easy to do without getting too into the weeds with you guys on some complex control systems. Yeah, because when we got really high, so the velocity controller is doing pretty good, actually. But the distance controller, so yeah, a bigger derivative term might actually improve that. Hesitant to do too much on that, but maybe something like that. Because derivative term will help prevent an overshoot, and it basically subtracts your derivative term. It basically gets subtracted, see, from your output. So yeah, that actually might be what I want. We'll try it and see if that does it. But of course, when you get into having too large of a derivative term, you can get some pretty weird behaviors, of course. But yeah, okay, let's try that again. Hey, what's up, Lava Lamp? Yep, it's our DCX vehicle, and we are fully automating it in Python, and it's going fantastic after that test, chat. Like, I'm good to wipe the hands clean, and let's bring on New Glenn. Let's bring on the New Glenn vehicle. Let's put people on it. We're good to go. It's ready, chat. Let's just put this software into New Glenn or Falcon 9. Okay. Let us now bump it. Actually, okay, before we do that, I'm going to do one more test at 15 kilometers altitude and see how it performs, repeatability and all that, right, chat? Make sure that the PIDs adding that derivative term will hopefully be good. And then from there, we'll start increasing, basically doing a flight envelope expansion campaign. We talked about that on, I think it was Thursday when we did our space news segment. Strata Launcher is starting to do a flight envelope expansion campaign, which is pretty crazy. You guys aren't familiar with launching tomorrow their New Shepard vehicle. It's its return to flight for crew, which is awesome. But yeah, I want to do Strato Launcher, or Strata Launch, right? Strata Launcher's the aircraft. Actually, their aircraft I think is Rock. No, this is a render, right? Yeah, this is a render. Wait, when was this? Oh, this was March 26th. Okay, yeah. Ooh. Chad. Okay, but this is what I was talking about. So it says, today the test team is conducting a functional check flight with Rock, focused on testing system upgrades to the Mission Control Center, flight deck, and training new members. This test is in preparation for Rock's upcoming Envelope expansion series that will take it higher for Talon A launch capabilities. Six 747 engines. Also notice all the 747s in the background, Chad. This is at Mojave Air and Spaceport. It's the massive 747 graveyard. That's a render. I thought it looked like it for a second just because the deployable vehicle looked a little weird, but I'll have to go back in it. I didn't read it. Look at that monster fly. Let's go public. Yeah, easy. Look at that, chat. What a beast. The APU gills, yeah. Yep. Ah, so good. But anyways, yeah, so that they're talking about doing a flight envelope expansion series, which we'll talk about here in a second, because what I want to see is, was that an actual render? It looks arguably fake, but you know, like this down here looks fake. This doesn't though. This doesn't look fake. That looks fake. We took a daring first step earlier this month with the completion of TA-1's first powered flight, reaching high supersonic speeds, approaching Mach 5. The flight was a landmark moment on our path to providing our customers and nation a reusable and routine hypersonic test capability. I guess not then. I have not seen this.
This is a new era.
What a beast, chat.
Today is the culmination of over 4 years of effort.
How they found those engines, indeed.
It's our first attempt at lighting.
Yeah, so Strata Launcher's first, I guess, go-to-market strategy is by focusing on a hypersonic testbed. Why? Because DARPA and every DoD organization out there wants a hypersonic testbed. So,
Sonic regime.
yeah, go figure, right? Testing hypersonic things.
The last time
Who would have guessed?
a reusable hypersonic flight test vehicle was the X-15 in the 1960s.
But
Look at that. They call that the Talon A. Why are the twin fuselages on Strata Launch so huge? Surely it takes away from the payload capacity. Yeah, it's a good question. I mean, there's a lot of reasons kind of like why you need that for structural load, in order to actually reach the ground, give yourself plenty of height. There are reasons for it, right? Currently currently it has a teeny tiny vehicle, but did you guys know that Strata Launch can actually carry a Falcon 9?
Bravo. Team's pretty excited. I'd say there's a lot of nervous optimism right now.
Hard to test hypersonic on the ground, true.
Have a good flight. Thanks so much.
You get to that point in a test program where...
Oh, look at that. Oh, Coyote. You better run, little coyote. I know, right, Lava? Like, this thing, I think, can carry 50 tons under the wing. Now, that's not a fully fueled Falcon 9, but it can carry in terms of its size. I'm pretty sure I remember seeing renders of that.
Green range.
Yeah, exactly. The height's required so you can get runway clearance to... How have I not seen this video, chat?
Ready.
Release, release, release.
5, 4, 3.
250? Oh, jeez. That was not a render. It looked so weird from that camera angle.
Stable.
There it goes. Rocket engine ignited. Oh, how awesome is that, chat? Dude.
Engine shut down. Good glide. Be advised we have a super experimental inbound for runway 30. All systems good for landing.
Super experimental inbound.
Today is many different departments.
Look at that, it lands one side down first.
And it's a huge day for this company.
The hardest part of this
Stratolaunch is a
that ensuring
beast,
that
man.
we have all the resources that the team needs, and there's no roadblocks.
Chuck Yeager did already do that, is true.
Quickly and as safely as possible.
I want to see that again. Holy cow, chat. That was wild. I've never seen this video before. Like, what?
Let's request range status.
Green range.
Copy. System 1, armed. System 2, armed. Looking for data. Good data. Good data. And pre-drop.
Yeah, but it's on a rail.
Now.
And typically when you want to test hypersonic things, you want to test the hypersonic control systems. And for that, you need a flying vehicle.
Release.
Why you want... Oh, that's so awesome. See, like that right there, it looks like a render. Like this doesn't look like a render, right? But that definitely looks like a render. Why? Because they're blurring parts of it. But that's why I thought this was just like a render from the company, like advertisement or whatever. But that's just crazy.
5, 4, 3.
See, they're blurring out all the cameras and stuff. Proprietary secret.
Stable.
Heck yeah.
Ignition.
That's wild, chat. That's awesome. I had no idea they did that yet. Where have I been? Under a rock, I guess.
That is amazing. Into the sun.
I like the ATC call out too.
Be advised we have a super experimental inbound for runway 30.
Super experimental inbound.
Good for landing.
Mojave Tower, Roger. Clear for the option.
Today is many different departments, many different.
Oh my
employees'
God.
work
What a
coming together,
beast.
And it's a huge day for this company.
The
And
hardest
you'd
part
fling the
of
test
this
bed on an arc?
is
Yeah, but you
ensuring
need
that
a
we
lot
have
of...
all the resources that the team needs,
Oh,
and there's
yeah,
no
I don't know.
roadblocks, and they can get this done as quickly and as safely as possible.
Well, of course, remember, again, chat, Stratolaunch is a commercial company looking to do space flight, air launch space capabilities, but their go-to-market strategy is to start with hypersonics. They also, I mean, if you guys look at the Stratolaunch website, you can already see a lot of their concepts unless they change them. They have Talon A, they want to do air launch platforms. They want to do like space air launch platforms. They should already have concepts unless they took them off their website. They should have concepts for much larger actual spacefaring vehicles too. So yeah, Rock is their aircraft, which is an absolute powerhouse. Spirit of Mojave, oh, the future vehicles is what I want to see. Spirit of Mojave, is this what they bought from Virgin Galactic? They bought this from Virgin Galactic, didn't they? Isn't this the same aircraft? Because somebody did acquire the Virgin Galactic plane. Was it Stratolaunch or was it somebody else? I don't remember, but yeah, go figure. And then future vehicles. Yeah, long ramp indeed. All right, so they should have concepts. Yep, so there you go. They want to actually build a space shuttle, because why not? And they also had a concept to be able to launch Dream Chaser. Yes, chat. They want to be able to launch Dream Chaser. This was actually a YouTube video. Can't click on anything. Awesome. This is from Haze Gray Art. Oh, awesome. Haze Gray Art is the bomb. Yeah, they were going to use a Pegasus rocket, if I remember correctly. Like an upgraded one. No, they didn't sell it off. They're still around. It just changed ownership or whatever. This was a real thing they wanted to do, by the way. When Dream Tracer was just getting off the ground. Well, I guess it's still technically trying to get off the ground, but you know what I mean. There it goes. And ignition. Oh my god. Could you imagine seeing this? How wild. Carrying people to space in a Dream Chaser like this. Air launch platform style. I like it. I'm a fan. But yeah, that was a real thing, and they got their first flight under the belt, which is pretty awesome. All right, let's test this one more time, chat, and see. We're going to 15 kilometers, and then we got to backtrack it, and we got to take it up to 60 and see how well it performs. Because I'm sure we're going to have to retune it for 60 kilometers altitude. It's too shiny, yeah. There we go. Take it on up. Stand by. We're about to enter our landing configuration as we fall through the atmosphere. I guess I should say our descent configuration would probably be the more accurate term. Seems more appropriate for solid fuel. Yeah. It was somebody's concept. I was thinking it was Pegasus, but might be a different one. I was thinking that they were looking to partner all of them. There we go. Stand by. All right, so we're moving away. We are pitching down at -23. Horizontal velocity controller is trying to pitch down even more. Awesome. And now we're going positive. Moving towards the pad. Starting to pitch up. Yes. Definitely trying to pitch up now. Super good. As we're 600 meters away. Still pitching up. It's not bad. Still pitching up. Holding that, chat. We are holding that. Really not bad. Could it be better? Yeah, it could be better. But honestly, I'm pretty happy with that. So what does that mean? The derivative term is too much? Methinks. We were still getting a higher pitch up relative to our velocity than we wanted to be pitched down. We might actually want to back off our stop it. It's right there. It's actually working though. So this might be too much because we increased it by 5 times. So if we do that by like that, then this by like that. See what that does. Okay. Let's bring it all the way up, chat. What do you say? Let's bring it all the way up. So our target altitude is now going to be 60, and I'm pretty sure it's not going to work from that point because it's way too high from where we're currently testing, but hey, you never know, right? You never know. Yep, could increase P. Could increase P. We did a little bit of both. We subtracted our delta, our derivative term a little bit, and then slightly increased P. All good. We'll see what that manages. Yo, what's up, Nova? How are you doing, my friend? Good to see you. Yeah, they did misadventures, indeed. There's they actually did that to see how abort contingencies would work for the crew variant. Dream Chaser Atlas 5 abort. There's actually a paper on it from somewhere. See if I can find there's actually a really cool oh yeah, there you go. Here's the actual render of it on the Atlas 5, but there was a paper that actually looked at how it would perform in a abort scenario with different launch escape system configurations. It's actually a really cool paper. These are just images though. Let's see here. Integrated configuration. Yeah, no, not that one. I love your practice. Well, thank you so much. I'm glad you're enjoying it. Maybe it's this one, achieving full ascent abort coverage, download PDF text. Let me see, what's this one? What do we got? Is this the one I'm thinking of? Yes, this is the one I'm thinking of. I think, yes. See, look. So there was original concepts to put it on top of an Atlas 5, on top of Centaur, right? And they would actually have this integrated boat tail that it kind of sat inside. And during an abort contingency, the engines would ignite inside this boat tail, and it had vents which allowed it to, well, basically not explode the Centaur, which is pretty cool. But yeah, this paper talks about all of the different operational contingencies for abort for the Dream Chaser vehicle, going through different thermal temperatures and all that sort of stuff. Yeah, pretty in depth for anybody interdasted. What a link that was. But anyways, yeah, an untested hostage. It's fine. Don't worry about it. There was a video about that as well. Yeah, indeed, Nova. Indeed, there was. All right, let's go. We are 60 kilometers altitude. That's our goal, chat. We are fully fueled. Vehicle is nominal. Let's see what we got. We're gonna time warp all the way up. Let's see how close our apoapsis estimation gets, because it works really good for short range, but I expect that as we do very long range approximations, there's going to be some inaccuracies, of course. But we'll just see how close we can get. Our goal is 60 kilometers. We did overshoot by a good little bit. Hey, what's up, Crines? How are you? Indeed. We've been at it for quite some time. Everything that you see that I'm working on is already on GitHub, except for what we're working on today. So feel free for y'all to check it out if y'all would like to do the same. All right, so we're coasting up at our mark of 67 kilometers or so. There we go. Let's see our readout. All right, looking good. We should see they're going to enter the velocity hold. There it is, entering vertical velocity hold. Entering state machine 1. And entering now our belly flop. And yeah, we'll see. Oh wow, we're actually only 600 meters from the pad and we're actually moving towards it. That's actually kind of interesting. How this one is so much different than the others. There you go. We're very, very close to it. Nice. All right, I'm digging it. All right, now we're moving away from it. Why would it overshoot so much? Because it's a lifting body and it generates lift, and so we are basically falling, and so eventually we turn that potential energy into kinetic energy and vice versa, and that now, because we generate lift and pointing nose down, we get a lot of horizontal velocity. Let's actually look here. I want to see my pitch indicator for when to activate my RCS. Yep, so we're maintaining a pitch down, trying to move towards the pad. Oh, for that, because we're only estimating, and the estimation is only as good as the information that you have, and we're estimating a lot of different parameters. We're estimating the drag on the vehicle, and those are not static, and so we're using a static number for that as well. So yeah. All right, we're moving towards the pad. We're starting to pitch up a little bit. Nice. Get a little wonky in our pitch because we're going so fast, but we are pitching way up, which is nice. It'll bring it back, I think. It's just the aerodynamics were too much for it. And remember, this is not a very aerodynamic vehicle, so it's just trying everything it can. Trying out everything that it can, chat, to remain where it needs to go. There we go. We're pitching up again. We are doing pretty fantastic, actually, all things considered. We are pitching up. Awesome. That's so good to see that we're pitching that far up. And now we should be entering landing config. Oh my goodness. So we went 60 kilometers and we're going to miss the landing pad by 100 meters. I like it. Fully autonomous at this stage too, so that's the automated landing burn. Bringing it right down next to the truck. That's fine, right, chat? That's okay. That's okay. And touchdown. Wow, that worked way better than I thought. There are no air fins at all? There are, but they are more like body flaps. They're more like body flaps. Okay. Pretty happy with that, actually. Pretty happy with that. And so, like, really the main thing to take away from here is that we just got to tune the PID. And I think if we can tune the PID to be really, really close, we should be able to get that repeatability. But there's only so much you can do with proportional integral derivative controllers because they're linear controllers, and your vehicle's not linear, chat, so it can only do so much. But I'm pretty happy with that. I'm actually really happy with that. We went 60 kilometers in altitude, and we came back and landed within, you know, I don't know, a couple hundred meters of the actual takeoff point. Yeah, of course I still lawn you, and exactly. Well, I think that's pretty good, chat. So unfortunately, I am going to have to end it right there. I know a little bit of a shorter stream today, but I've got to go for some evening festivities. So much love to all of y'all for hanging out. Apologize for the shorter stream, but I'm thinking I'm probably going to stream tomorrow as well, and we'll see what trouble we can get into tomorrow in KSP as well. But with that, chat, have a much wonderful rest of your Saturday evening. We will be back here hopefully tomorrow, picking things up where we left off and seeing what more we can do. So with that, I'm out. Have a good one, and we'll see you tomorrow.